All right, hello again there, data management folks. This is the review video on Chapter 6 and perhaps Chapter 7 if it doesn't get too long. We'll squish all that stuff into one video. This video is on probability. We see the topics that we covered there. Remember, all the formulas will be on your formula sheet. And let's get into it. The first example, typical introductory probability example. We've got a case, there's 132 tickets sold, 46 couples tickets. Notice right away you think that's 92 people, right? Were bought, and 12 people went on a carriage ride. 4 of the couples went on a carriage ride. If a prom goer was picked at random, state, here we go, the probability of picking a person from a couple. So if A is people are from a couple, well, then this is where we started in probability, these easy little formulas here. The number of couple tickets was 92 out of 132 tickets sold altogether. Jam that into a calculator, and that's about 73%. And for all of these probability questions, you should have a closing sentence, therefore, blah, 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 blah. You should do that, and I'm saving time and effort doing that on the video. B, the odds against picking a carriage rider. Well, odds against something, tiny little formula, the probability of that not happening to the probability of it happening. And this, the event would be a carriage rider, right? So how many carriage riders do we have? Altogether, we had 12 people that went on a carriage ride. So that means there were 12 out of 132 tickets, where if I subtract that, that's 120 people who did not go on a carriage ride in total. And then, of course, we don't leave odds like this. This is a mess. The bottoms will actually cancel out, and it's 120 people to 12 people, or 10 to 1. That's the odds against we pick somebody who went on a carriage ride. C, the probability of picking a couple given they are a carriage rider. Here we go. So that's the probability. We pick a person from a couple, not a couple of people, given they are a carriage rider. And so I'm using the same events I defined in A and B. And that formula, this is conditional probability, is the probability of both things happening over the probability of the second thing happening. Again, check it on your formula sheet, folks. Get used to using that formula sheet. Here, these things are things that are in the question. And the probability that we have both things, well, both things happening is, well, there were 4 of the couples went on a carriage ride, right? 8 out of the 132 people, where the carriage riders was, what was it? It was 12 out of 132. So if I wanted to do this probability, it's 8 over 132 over, probability of B here was 12 over 132. Again, the bottoms will cancel out. 8 over 12, which is about 67%. So some of you might be saying, well, why didn't you use this formula? Because I remember that one, right? The probability of both things happening is the probability of A times the probability of B. Well, remember, that's if they're independent, right? And the question here is, of course, are they independent? Are these two events independent? And that was the little, I'm going to change my color here, why not? This little question there, and I'm just going to discuss it. Are the two events mutually exclusive? Mutually exclusive means, so, is it possible for them to happen at the same time? And if the answer is no, it's impossible for them to happen at the same time. They're mutually exclusive. So are these two events mutually exclusive? No, because there's eight people that were in both a couple and horse and buggy carriage riders. So no, are they independent? You know, the question you ask yourself there is, do the events affect each other? Do the events affect each other? Well, that's a harder question. The whole idea is, you know, does that extra information of knowing that they were a carriage rider, knowing they're a couple, change the probability of the other one? Well, we know that this probability was 0.67. The probability of A was 0.73. They are pretty close, but they are not equal. So these are not independent events. These are dependent events. Okay, on to the next example. Example 2. There were 12 people on prom committee. Miss Craig randomly selected 4 people to get gift certificates as a thank you. What is the probability that Fredette wins a gift card but Draft does not? Okay, so I'm just going to, this is Fredette but not Draft. Get gift certificates. Okay, that's the event. You notice this is a counting problem. They're just whether people get the gift certificates or not, so order is not important. So that means this is a C question. So I think this one, although we could probably think of it as one of these combined event problems, but I think it's just is easy to use our counting problem. So what's the number of ways in total? Number of ways in total is, well, there's just 12 people, and 4 of them get gift certificates. That's it. This is 12, choose 4 on the bottom. On the top, it's actually a little bit more difficult, right? So we kind of got a few things to figure out. Well, if Fredette has to get a gift certificate, that means she's selected. Draft does not get a gift certificate. And then how many people do we have in total? Well, we have 12 in total, so that's going to be 10 choose, 3 more gift certificates to give out. And then I multiply those all up because I got choices for Fredette, choices for Draft, and choices for the rest. Remember that the idea of a restriction is you satisfy the restriction, fill in the rest. And that is the top, which is 1 times 1 times 10 to choose 3. Jam that into a calculator is 120. So I got 120 over whatever 12 choose 4 is. 495. You can write that as a percent. It's about 24%, and there's your closing statement. Onwards. Again, if I'm going too fast, pause the darn video. Can't ask questions? Pause the video. Of course, in these videos, if there's something that you're not sure, write it in the margin and ask in class, or come visit me for extra help during exams. All that stuff works fine. Here, Ferd is a frustrating friend to have on prom night. He said he was only 80% sure that he was going to go, and then 75% sure he'd chip in for the handsome cab. If he did go, there's a 10% chance that he'd chip in even if he didn't go. Well, this is this idea of dependent events. One event changes the probability of the other. So it says to define some events. A is going to be the fact that Ferd goes or not. Notice that we wouldn't define event B to be that he doesn't go, because that he doesn't go is just a complement. Right? And so we think this, we're not going to write it down, because B is the probability that he chips in. And it says make a probability tree. This is more like a tree diagram. I'm going to do it in black. Why not? And I'm just going to do this freehand. You should do this with a ruler. He can go or not. He chips in or not in both cases. And of course, these aren't equally likely events, right? The probability that he goes, he says he's 80% sure, so that means he's 20% thinking that he's not going to go. If he goes, he's 75% sure he's going to chip in, which means if he goes, he's 25% not going to chip in. If he doesn't go, he's going to chip in with 10%. Why he would do that, don't know. maybe Ferd's a nice guy, so that leaves 90%. And so overall, what's the probability that he chips in? Well, that means it's this path, right? This path here, or key counting word, right? Key counting word, or this path. Well, to get to this path here, this would have to happen, and that has to happen. Well, that and means multiply. That's to get to this path. Or means plus. To get to this path, this has to happen, and this has to happen. 0.2 times 0.1 in total. Jam that into a calculator, 62% chance. 0.62, and then of course there's your closing sentence. There's some decent examples for chapter 6. Let me check the time, see if I should just keep going. No, I'm going to pause it or stop there. And video 2 for day 3 of review here will be chapter 7.